You're listening to a CNA podcast.
If you are an avid traveler, you know by now that you can't bet on the weather. Some places that are in the depths of winter can have warm days, or you could get caught in an Arctic blast or a bad blizzard, leading to all kinds of travel chaos. The shifts in climate are not just altering our weather patterns and affecting travel plans, they might have a more sinister impact on infectious diseases. In Southeast Asia, the surge in dengue cases has been attributed to longer rainy seasons and more severe floods. North America is seeing an expanding range of ticks carrying Lyme disease due to rising temperatures. And the warming climate in Central Africa is creating more favorable environments for bats and other potential hosts of Ebola. To explore this complex interplay between climate change and infectious diseases, we are joined by Dr. Mary Rodgers, who's a key member of the Abbott Pandemic Defense Coalition and an accomplished infectious disease researcher. Dr. Rodgers, delighted to have you on the show. Thank you so much for joining us.
My pleasure. Thanks for inviting me.
Many call you the virus hunter. That's quite a title, I must say. Tell us about your work.
A virus hunter is kind of a mysterious sounding term, so I'd be glad to break it down a little bit. It's definitely as exciting as it sounds. So here at Abbott, we've been studying infectious diseases for decades. We actually have a really strong leadership in studying viruses in particular, because we launched the first FDA-approved test in 1985 for HIV. And that was a really big deal because it changed the trajectory of the HIV pandemic. And we've continued to make new observations about that virus since then. And we've learned throughout those decades that there's one thing that we can always be certain of, and that's that viruses will continuously change. They don't slow down, they don't rest, they don't take a break. And that's why we have to be faster than them. And so that's how we've been able to launch our Abbott Pandemic Defense Coalition on that legacy of studying infectious diseases and responding to COVID, because we really need to be vigilant. We need to be monitoring how viruses are mutating, what's popping up in different parts of the world, so that we can be able to respond faster than ever before.
So I wonder, when did climate change come into the picture? Was it like a gradual entrance, or did it burst into the scene?
Climate change is always affecting how viruses spread. And it's something we've always been aware of throughout the decades, really, because where pathogens are spreading is largely driven by where animals live, where insects like ticks and mosquitoes live and thrive. And we have seen changes over time in the trends where mosquitoes and ticks can survive, that footprint that's been growing over time. And so we've been watching those changes over the years. Particularly, we learned from COVID that a virus or a new strain of a virus can cross borders within days. So we're seeing that even as something might be affected in one part of the world due to climate change, it can rapidly dissipate around the globe, depending on what it might be. And so we keep a very close eye on how things that we would have expected to behave one way might actually be different because of climate change.
So here's something I've read. The climate change doesn't produce disease itself, but rather it serves as a multiplier or a catalyst in increasing the speeding of the threat and disease emerging. Could you explain to us why changes in our climate act like a fire starter at a barbecue, so to speak?
It's an interesting way of putting it, because you're right, climate change itself does not actually transmit diseases. But what does are things like increases in precipitation. So suddenly there's more flooding, and now water that carries pathogens is closer to people, and that's how people get sick. And places where they might not normally had an exposure because they didn't have a flood as frequently as they do now. We also see that as temperatures rise, mosquitoes that transmit, spread virus like dengue, for example, higher temperatures actually allow that mosquito species to bite more than they normally would. The multiplying effect of that is immediately obvious because you have more people getting infected from the same mosquitoes. So those are some of the examples that we see. We actually have seen that over half of all known pathogens can actually be affected by climate change in one way or another. And so that means that we have a pretty big challenge ahead of us as things become less predictable due to all of these changes in the climate. And that's why it's really important to have a program like the Abbott Pandemic Defense Coalition, where we have sites on 20 different countries around the world on 5 continents on the ground, working with people who are sick, trying to understand what's causing their illness. And then if we can't determine a cause, we actually have a new technology that we apply called metagenomic next generation sequencing, which is a big long phrase to essentially say, we look at every single nucleic acid, RNA or DNA of a genome in a sample, and we can figure out what is making someone sick. And so by being able to look at everything in an unbiased way, we can now say, well, maybe they weren't tested for malaria, but that's actually what's making someone sick. Or we've really found something completely new. We need to start preparing for it.
Wow, that's a very intricate crossway of climate and health and science all together. I just loved how you gave us an example of that specific climate hazard that had led to aggravation of epidemics and pathogens, and namely heat 2024, maybe even worse. Could you maybe give us a bit more examples on how heat or heat waves in particular could contribute to the increased virulence of pathogens?
So the pathogens themselves are able to mutate more depending on how many hosts they have, if you will. So if you think about COVID as an example, the more people who get COVID, the more opportunities each individual person who has COVID is giving that virus an opportunity to mutate and change and adapt. So if we have more outbreaks, if we have more opportunities for pathogens to be able to make more copies of themselves and change every time they do that, then that could potentially fuel the ability of these viruses to potentially jump into a new host or start to have a new transmission path. And when we look at the sequences, which is what we're doing in the coalition, we're able to really look at that and see how parts of the virus that are under pressure to change are mutating. In fact, one example I could share is how we've looked at a virus that's called picovirus. So this is a virus you probably haven't heard of. We hope it stays that way. So it's typically causing gastrointestinal disease. So it'll cause diarrhea. It'll make someone sick to their stomach. And so those kinds of diseases don't usually kill people very frequently or cause pandemics necessarily. But what we were really concerned about was when we started to see strains of this virus appearing in people who had been hospitalized for acute respiratory illness in Colombia. And so we applied our whole method that we use in the coalition, where we start by sequencing and looking at everything there. And we found picovirus. We thought, that's odd because usually that's not found in someone's lungs. So then we went on to understand, we built a prototype test because testing is really key when you find a new pathogen like that. And we screened to look at other cases where they didn't really find the diagnosis of what was making someone sick for respiratory illness. And we found 25 more cases in 2 countries. So this was in North America and South America. And then when we looked at the sequence database, we found there were actually some older cases from 2009, 2 of them being in Cambodia, 1 of them being in China. And so those were the most common ancestor strains. But the virus had evolved and it actually mutated, and it had gone through a cycle where it had replicated in great-tailed ducks, Tasmanian devils, and rabbits living in Australia before it really expanded to have this ability to cause a new type of disease in humans.
Wow.
And so tracking all that is based on the sequences and based on the clinical presentation. And so having a really good idea of how sick someone is and what pathogens are causing it is how we kind of start to unravel all these trajectories that we wouldn't have known about otherwise.
So what are the odds of the next pandemic being fueled by climatic factors, would you say?
We really are facing an era of pandemics. And with the climate changes that we're seeing, it's highly likely, knowing that half of all pathogens that we know about today are going to be impacted by climate change, that is going to have an impact on what the next pandemic could hold for us. But I also know that every outbreak is different. And if COVID has taught me anything, it's not to try my crystal ball per se, because we can't really predict very much. In fact, if anything, climate change makes things a little less predictable in terms of what the next pandemic could look like. And so what it's really important is to prepare for that. Even though we don't know what it's going to be like, if we're able to do the work we can do today to prepare for something, then we can hopefully stop something that could be emerging in its tracks before it becomes a major pandemic that impacted everyone's lives the way COVID did.
So we talked about heat. Maybe we can go specifically about storms, floods, and sea level rise. How do they worsen the epidemics or an infectious disease and the transmission pathways involved?
That's a really interesting question because as we have more precipitation and sea levels start to rise, we have flooding, we have a lot of displacement and movement of people. Because if people can no longer live in places that are prone to being impacted by increasing water levels, then that causes people to move. And now we have areas where, for example, in our coalition site in Colombia, there's a part of the country near the Darien Gap where there's a lot of migration of people from all over the world who are coming towards North America. People are coming from Africa, Europe, Asia, and South America, all converging in this one part of the world before they head northward. And so that displacement of people and migration can lead to rapid spread of pathogens that wouldn't normally be able to go from one person to another from all these disparate locations. And so that's one way that flooding is affecting people and then affecting how pathogens spread.
Speaking of the pathways, does that mean how climate change drama unfolds in, let's say, a remote island in Borneo? They deal with different sets of disease and challenges compared to densely populated places like Singapore?
There is definitely a different type of pathogen milieu, if you will, in different regions of the world, just based on what the climate is and what kinds of animals and bugs are living in the different areas. We also know that people who have a high closeness to animals, so people who either hunt or farm, who are closely handling animals who might be sick, have a higher likelihood of potentially coming into contact with pathogens that could make people sick and spread more broadly. And so we see outbreaks from time to time, and then things that people who have contact with animals don't necessarily spread to other people. But if that were to ever change, a more densely populated area could be more affected potentially because people are closer together and it's easier for something to spread. We really saw this happen in real life recently with COVID. And that's where we learned a lot about how important testing can be. So once we were able to determine who had been infected, then if we had tests right away in a more regional area where there wasn't a lot of opportunity for transmission, then that would allow us to hopefully contain something before it spreads to a place where there's a higher density of population. And I know that the average person might not have an awareness, but it's very difficult to build a really good diagnostic test that will hold up to the demands of these kinds of scenarios. And so because we have all this expertise, our pandemic preparedness program here at Abbott, the APDC, is in a good position to be able to not just look, but also respond when things like this happen with prototype diagnostic tests, which really are important so that we can answer those key questions right away about how far something's already spread, who's at highest risk. And then that can fuel public health responses where the right decision makers can now have the information they need to do things like mosquito abatement or isolation if needed.
We'll definitely talk about those strategies later in our conversation, but I wonder, are there specific climate-sensitive diseases that you think should be prioritized to better prepare for emerging threats? Do you have top picks at Abbott?
Well, they could all surprise us. So with that caveat, I think of it more in terms of the vectors as opposed to the actual pathogens themselves. So diseases that are spread by ticks are something that's not necessarily on everyone's radar because the climates where ticks thrive have stayed the same for a really long time. But I am very worried about a lot of rare diseases that are spread by ticks that as that area where they can thrive is changing, that we could see a lot of unusual pathogens now starting to emerge because of the tick population. So I live in a tick endemic region where ticks are tiny little bugs. They live primarily on animals, but they will drop from trees or other high areas and land on a person and crawl around till they find kind of like a hidden area where you won't notice them.
Oh, no.
And it will bite. And that bite is what causes pathogen to transmit. So it becomes a blood contact with the tick. It's a different mechanism. The type of bite is different than you would have with, say, a mosquito, which I'm sure you're very familiar with. Mosquitoes, we have a lot of those too, and there's many different species of mosquitoes as well. And so the different species of all these different bugs have different pathogens that can survive in them and be transmitted through their bite. And so as those insects now have a different footprint, that's where I want to keep an eye on what could be coming through those bites.
All right. So, Dr. Wee, we talked about the negatives. Could a climate shift have a positive side? I mean, could it actually be a good thing? I imagine, for instance, we've been talking about mosquitoes. So, lack of water may lead to fewer mosquitoes?
There are some regions where it will become too dry for mosquitoes, but coupled with higher temperatures, I don't know if that's necessarily a good thing.
Okay.
I know that that is appealing to maybe have no mosquitoes, but then it's also really uncomfortably hot for humans. And when it's that dry, it could be really dangerous. So I think anything we can do to help not only mitigate the impact of environmental changes, but also to be able to monitor how pathogens and vectors like mosquitoes and mites and ticks are changing are things that we can do today to try and hopefully prevent this from actually being a disaster in the future.
So let's talk strategy, Dr. Rodgers. I mean, disease taking a huge toll on healthcare resources. How big is the work of scientists like yourself to healthcare planners and policymakers? What do they need to know?
It's really important to take the lessons that we learned from COVID and apply them so that we're better prepared for what could be coming next in terms of pandemics. And what we do know is that if we take better care as a healthcare system of those who are most vulnerable and get a correct diagnosis for everyone who is sick and treat them and take care of them, then we'll all collectively be healthier when whatever pandemic comes next arises. And so that's where we think that we have all the tools we need right now to be able to do that kind of work, to deliver that healthcare and to deliver those tests and get definitive diagnoses. And once we know what's currently circulating, it will be a lot easier to spot when something's different that we need to act on differently.
Any hotspots on the radar, some places that are more vulnerable than others?
That's actually an interesting point. That's one of the aims of our Pandemic Defense Coalition here at Abbott is to try and increase the infrastructure in regions where there might not be as much capacity to monitor infectious diseases. And so we're training people to do the methods that I talked about earlier, that sequencing method to look at everything and to run these prototype tests so that they're better able to respond in regions that might be more vulnerable. When I think about regions that could be hotspots potentially, I think more along the lines of where there's a high level of biodiversity and where there's a high level of human migration. So where people are moving most. And those are regions of the world where there's a lot of immigration or there's a lot of travel. Global travel is definitely one of the ways that we could see something spread. And so there's a few places in the world where those criteria could be met. And some of them are on most continents, but mostly around tropical zones.
Obviously, we can't predict the future, well, at least not with precise certainty. But what do you see as the biggest challenge or the biggest obstacle in your line of work?
In my line of work, I think the biggest challenge is being able to respond fast enough. We're doing everything we can to be able to respond faster than ever before. And we have done it. When there was an Mpox outbreak, for example, we were able to make prototype tests and get them out in a matter of weeks. But every day counts when it comes to a pandemic. And so we think about this all the time. What could we do to get faster by even one more day? 2 more days. We really need to do everything we can because every day counts when there's people being affected by a new pathogen that's on the loose. We probably need to think of new strategies to be able to make a difference because we actually found during COVID that we could act faster if we did several things in parallel that we needed to do to develop a prototype test and then launch it as a diagnostic. And so that's just one example of how we were able to move faster just by changing how we were doing things. I think there's a lot of more opportunities to work more efficiently. Some of that involves communication too. And that's another thing that we're trying to work on in our coalition is because we have these sites around the world, we're able to rapidly share, hey, this is what we're seeing in Senegal, for example. What are you seeing in Thailand? And compare and actually see if there's some similarities that we could act on quickly.
In your assessment, is the world adequately prepared or ready for climate change-driven outbreaks?
We're as prepared as we've ever been before. We have more tools at our disposal. We have more technologies than we ever have before. And I would say that we're in a good place to be able to respond quickly I actually like to tell people that I can sleep well at night because of the network that I'm part of. The people I work with are passionate about being able to respond and sense new trends in infectious diseases. And knowing that we are all working around the clock, even when it's not an emergency, really helps me rest and hope that we're leaving a better place for the future generations ahead of us.
Speaking of the future, what are the most efficient ways to prevent the next global health emergency, and how can we cut off pathways for disease transmission?
Looking ahead, I think that one of the strategies that we'll want to use is to do broadly more testing. If you have a definitive diagnosis, for example, and you know for sure that someone has strep throat, for example, and not COVID, then you can treat them with antibiotics and they'll resolve and they won't pass it on to someone else. But if we never test people and we never really find out whether it was the flu or not, or we don't really know what caused someone's illness, then that just gives a pathogen more opportunities to spread silently and infect more people before we really understand the problem. And so that's where I think using the tests that we have today for all the known pathogens can really help us a lot, because that helps us understand what else might be out there and recognize it sooner. In fact, one of our sites at Mahidol University in Thailand has a vault of decades worth of cases they've been saving that were mysteries. They couldn't figure out at the time what was making people sick. So these are people in the hospital with a fever that they never really found out what the diagnosis was. And so we've gone back and looked at that library of samples. We've actually found that about 40% of them, we could find the pathogen and identify it. And it was something that hadn't been tested for at the time because they may not have had tests, just going back 20 years or so. And so we're able to find things like some cases of chikungunya virus or even HIV. There's also the 60% or so that we couldn't find something in, and that might be because it might not have been due to an infectious disease. But we're solving a lot of mysteries with that 40%. And so now we kind of have a reference point with what has happened in the past so that we can then compare it as we find new things in the future.
That is fascinating, Doctor, and sounds like a great strategy and ultimate battle plan, so to speak. So thank you very much for coming in today, sharing with us, helping us understand the dynamic intersection of climate, health, and science. Thank you.
Pleasure to be here. Thank you, Julie.
But many thanks to Dr. Mary Rodgers and to our listeners. We hope you enjoyed this episode. The team behind this podcast is Tiffany Young, Cyan Nguyen, Joanne Chan, and Crispina Robert. Till we meet again next week, I'm Julie Yoo, signing off.